Hello everyone, I'm Maximilian Probst Gutenberg from the ETH Zurich, and this is joint work with Bernstein and Thatchaphol Saranurak, and I'm going to talk about the problems of reachability, SCCs, and shortest paths, and how to maintain them in decremental graphs deterministically. And in particular, I'm going to talk about two techniques that help us to achieve a new result, and these techniques are directed expanders and congestion balancing. So I'm going to start slow and just introduce the problems. I'm going to start with the first problem, which is called the strongly connected components problem. Here you're given a directed graph G, and you say that any two vertices U and V are strongly connected if there's a cycle containing them. So, for example, here the red edges form a cycle and U and V is on the cycle, so these two vertices must be strongly connected. Another way of saying that is that U reaches V and V reaches U. That also means that they are on a cycle. Now, the strongly connected components, the SCCs, is just a partition of the graph of the vertex set into a maximal set of vertices that are pairwise strongly connected. So what does that mean? Essentially, one way to get the SCCs actually is to just find cycles and contract them, and then all the vertices that you contracted into one component are strongly connected and form an SCC. And this is a unique partition. And this problem is well understood in the static setting. Tarjan gave an algorithm that runs in linear time in the early 70s. Now the problem we want to consider here is what happens if the graph is actually not static, but is undergoing a sequence of edge deletions. So this means that this turns the whole problem into a data structure problem, where you want to input into your data structure deletions, and you want to have a second operation, which is queries. So the deletion, you want to give an edge UV, and that edge should then be removed from the graph, and the query, those can be completely two different vertices. Let's also say UV, and you then want to know, are they strongly connected in the current version of G? So for example, initially we know that U and V are strongly connected, and now I might remove an edge, but still U and V are on one big cycle. So this means if I query, they should still be strongly connected in the current version of the graph, but then an edge deletion might mean that I cannot reach from V to, I cannot go from V to U anymore. So the strongly connected components change, and I now know that U and V are no longer strongly connected. And therefore, if I would now query the data structure, it should return this answer. And a kind of related problem to this is the decremental single source shortest path problem. So here you're actually fixing a source in the beginning, the source vertex S. And then the data structure problem is kind of similar in the delete operation, but in the query operation, you now only input one vertex, the vertex V, and then the query operation returns you the distance or approximate distance from S to V. So on the right-hand side, if this was a unit-weighted graph, then the distance from S to V would be originally 1, but then if you delete the edge that goes directly from S to V, the distance would jump up to 4. And even if you return approximate distances for a reasonable approximation, you should actually already get a change in the query. Now, I want to talk briefly about the motivation for these problems, since it is kind of particular. So first, one reason why we want to see these decremental data structures where you undergo edge deletions is that they serve often as building blocks to fully dynamic problems where you have edge deletions and insertions, and often the decremental, so the edge deletions part is the harder part, and you can then lift it to the fully dynamic setting. This is true for fully dynamic APSP and transitive closure, for example. Another motivation comes from model checking and simulations. There's a whole bunch of things you can try to emulate with these algorithms. And what often happens is that, especially for strongly connected components, that you want to detect a moment in time where your graph no longer forms one big strongly connected component, but breaks apart. And finally, one huge point of motivation is that you could actually derive static algorithms for max flow, multi-commodity flows, sparse cuts, so all kinds of cut and flow problems using the MWU framework and a really powerful SSSP data structure. Now, next I want to talk about the results here, and I'm going to start with the algorithms for the Deterministic Decremental SCC. This is also for reachability, really, but single source reachability. But since it can be reduced to SCC, I will not talk very explicitly about it. So for the Deterministic Decremental SCC problem, the first thing we had is really by Even and Saranurak data structure from the 80s that ran in total update time MN. So total update time means the time to process all the updates until the graph is empty, and you can just specify the sequence of these M edge deletions arbitrarily. And that data structure that achieved all of MN time by Even and Saranurak was actually only for single source reachability, so it couldn't even handle SCCs. But then Wonsky actually came up almost 40 years later with quite a clever way to bootstrap this and to actually get SCCs using MN time, total time. And this MN total update time is often seen as a fundamental barrier for these kind of problems, also in the randomized setting. And in this talk, I'm presenting the first improvement of that goes beyond that barrier. And this is just a first improvement, I guess, but the total update time we show can actually be decreased to MN 2/3. And I just want to point out that this is for deterministic, and in the randomized setting, we actually do have a better understanding. In particular, last year, we presented an algorithm together with Bernstein and Wolf-Nielsen that runs in near linear time, total update time for SCCs. So there's a huge gap in between these two algorithms. And it looks even bleaker for the Deterministic Decremental SSSP setting. So really since 1981, the Even and Saranurak data structure gave total update time. And for the SSSP problem already, but ever since it could not be improved in the deterministic setting. And this paper really is the first improvement, and it's an improvement for dense graphs only, but it does break the MN barrier for these very dense graphs, with the new total update time being N2 + 2/3. And I'll also point out that in the randomized setting, we don't completely understand this decremental SSSP problem, but there's actually an algorithm that runs in N² time, and that is actually also presented at Fox this year. Now I want to show you how to get actually the decremental SCC structure, at least from a very high level perspective. And as a warm-up, I'm going to talk about how to achieve running time M1 + 2/3. So later we will get MN 2/3. So this warm-up will present you with techniques to actually get it to break this MN barrier for very sparse graphs already. And later I will show how to refine it to the denser graphs. And the technique I'm going to talk about here is really directed expanders. So for that, I want to recap briefly the undirected expanders. So undirected expanders, for that, you really need to know the notion of a sparse cut. A sparse cut S, where S is like a set of vertices that have at most half the volume. In an undirected graph, we say is phi sparse for some parameter phi if the number of outgoing edges from S, so delta S, is smaller than phi times the volume of S. And if you look at the example graph below, you can see that actually S seems to have a lot of edges going to not S. And this means that for a reasonable phi, this should probably not be a phi sparse cut. And one family of graphs that we are very interested in is phi expanders, and those are graphs that do not have a single sparse phi sparse cut in the entire graph, no matter which cut you take. So intuitively, they're really, really well connected. And there's the celebrated expander decomposition, which has been used a lot during the last years. And phi expander decomposition is essentially that you're given a graph G, and then you want to find a vertex partition x1, x2, x3, such that each induced graph on a vertex set, so G of xi, for example, is a phi expander, and in the end, you only have phi, like order phi m edges that are not contained in any of these induced graphs. So those are edges that go in between expanders. And just for a brief illustration, you could, for example, have such a graph, and then it's very clear what to do. You would take these red edges for these edges that go in between expanders, and complete graphs are very well connected graphs. So you would make those expanders, and thus you would get a very nice expander decomposition here. Now let us carry that intuition over to directed graphs, or at least try. I'm defining a directed sparse cut. So here again, you're given a vertex set S. It only has half the volume at most. And then we say that S is phi sparse if the number of outgoing edges or the number of ingoing edges is smaller than phi times volume S. So in particular, this cut below that we see between S and not S, before it was in the undirected setting, we had a lot of edges going between S and not S, and that led to the conclusion that they are really well connected. But now it could mean that you can go very easily from S to not S, but it might be the case that you can actually not go so easily from not S to S. Here all the edges are directed in one direction. And in this case, we want to say that this is actually still a sparse cut, because you have no incoming edge to S, so for any phi, this should be a phi sparse cut. And we define a directed phi expander, just like an undirected phi expander, to be a graph that has no directed phi sparse cut. And now the question is, and this is something that has not been stated before, so it's also a conceptual a new concept, and that is, can we get some form of directed phi expander decomposition? And we showed that you can actually get something that is kind of close to a phi expander decomposition in undirected graphs. So here you're given, again, a graph, you're partitioning it into sets x1, x2, x3. Each xi is a directed, like the induced graph on xi is a directed phi expander. And now you have two components. So first, there is a set R of at most phi m edges. So these are excess edges, or the edges that go in between expanders that you know from the undirected setting, such that after removing these edges and after contracting all the expanders, you're left with a DAG. And this is quite a bit to swallow at first, maybe. So I have an illustration. So here I made the complete graph from my example before. I made them bidirectional. And here you can see one way to take such a decomposition. So intuitively, you have only a few back edges, the red edges, and a lot of forward-going edges in some sort of DAG. And if you would take this graph where you really contract the expanders, then you can now see that after removing the red edges, I'm left with a DAG, because these expander graphs can now be sorted. All right. Why are we talking about directed expanders in the first place? Well, the reason is quite simple. If a graph is a phi expander, a directed phi expander, then it's certainly a strongly connected component. If it's well directed, if it's well connected in this sense, then it means that you can go from from S to not S very easily, and vice versa. So in particular, I state this corollary here that given a directed phi expander decomposition for G, then the underlying partition is the set of SCCs in the graph G minus the set of the back edges R. So in particular, after taking away these R edges, these edges in R, my expanders are the only SCCs. And yeah, I'm idealizing slightly, but actually this is something that is very close to what we get. We can show that you can, for any phi, given a decremental directed graph G, can maintain such a phi expander decomposition with R being a decremental set, phi m edges, in total update time m over phi squared. And once you're given that, it's actually all you need is some kind of heavy lifting that is done by the data structure of Wonsky. And this helper theorem that I stated here tells you that if you have a graph G and you have a subset of vertices S and a data structure that maintains the SCCs of G minus S, then there exists an algorithm that can kind of lift these SCCs of G minus S to the SCCs of G in times M times S. So there's an additional time on top of maintaining the SCCs of G minus S. And with this in place, all you need to do really to get our result is to balance. So we would choose phi to be 1 over m 1/3. And then you can see that in the theorem 1, you will produce a set R that has size m 2/3. So R is never larger than m 2/3. And if you put the endpoints into a set S, so this set of vertices S is never larger than m 2/3, then also the helper theorem will allow you to lift the phi expander decomposition to the SCCs of G in time m1 plus 2/3. All right, this concludes the first section, and I'm now briefly going to cover how we get mn 2/3 total time with this new technique that we call congestion balancing, and that we believe or hope that it has a lot of applications in the future. So the main problem that we encounter is that we are using sparse cuts with regard to the volume, and the cuts are in terms of the edges. But when we look at Wonsky's theorem, really it would be convenient to get vertices right away. So we could say that, so we could instead define directed vertex sparse cuts, and we could say that a cut S of vertices again is phi vertex sparse if the number of, if the out neighborhood and the in neighborhood, or the out in neighborhood of S is smaller than the number of vertices of S times phi. And this gives rise to a directed vertex phi expander, just in the same way as we defined phi expanders. And then you can actually get a directed phi vertex decomposition. And here the key thing is that the set R is no longer going to be a set of phi m edges. It's now going to be a set of phi n vertices. So here you're actually gaining a factor of m over n. And with this in place, if we would get this, then we would be in much better shape for dense graphs. But the problem is that even in undirected decremental graphs, we would not know how to maintain a vertex phi decomposition. And one of the reasons is that you need to re-embed periodically expanders to show that they are still expanders, and that currently takes, to maintain a vertex phi expander decomposition, m squared over n phi squared time, which is a lot. And what we show is that if you use a special technique for embedding expanders, you can actually get the same total update time as for a normal edge expander. So in particular, we give for a decremental directed graph G, we can maintain a vertex phi expander decomposition with an incremental set R of vertices of at most phi n vertices, in total update time m over phi squared. And once you're given that, you can actually rebalance the term in Wronski with Wronski's algorithm, and you can now set phi to be 1 over n to n 1/3, and then the total algorithm update time becomes mn 2/3. So let me briefly go over a summary. What does this paper do? Well, we break the OMN barrier for deterministic decremental SSR, SCCs, and approximate single social paths in this paper. We introduced new techniques. First, we introduced techniques for expanders in directed graphs, and I think these will hopefully have a lot of applications also in the static setting. And we introduced a new technique called congestion balancing for expanders, and this is a technique that helps you to maintain vertex expander decompositions very efficiently. And this concludes the talk. So thank you very much.